Hello and welcome to Disseminate, the Computer Science Research Podcast. Today is another episode of our Cutting Edge series, and I'm going to be joined by Marco Costa, who will be talking about his recent paper from SIGMOD, Graffiti, Taming Adversarial Queries with Optimal Range Filters. Marco is a research engineer at Huawei. Welcome to the show, Marco.
Hey, thank you, Jack. Thank you for inviting me.
Yeah, I'm really looking forward to this chat today. So we always start off on the podcast by getting you to tell a listener more about your story and how you ended up being interested in database research. So yeah, tell us more about yourself, Marco.
So why database research? Our research about Graffiti, it's mainly a matter of algorithm engineering, right? But since this is a field that goes its main purpose about range filter, about what Graffiti is mainly because of database purpose. It's mainly used in database. And so when I started this work as my master thesis back in 2022, I had no idea about database research. I was just a master student. And then this work drove me straight into it. It started like a pure algorithm engineering work, an algorithm engineering thesis. But since this is a field that it's really used mainly into databases, then that's what I had to start studying about it, trying to implement Graffiti in modern databases, and that's basically how that started.
Nice, yeah. So you kind of found a back doorway into databases there, but now you've got the bug, right? That's it. Databases for life now. Cool. So we're going to be talking about Graffiti today. So let's set the listener up with some context for this chat then, because the title has some cool words in there like adversarial queries and optimal range filters. So
yeah,
let's kick things off, Ben. Tell us what our range query is, and yeah, what the heck is an adversarial query?
Basically, what range queries are is simple. You have a set of keys, and you want to check if a set intersects with those keys. So you have two endpoints, A and B, and you want to see if there is any key of your set that intersects on it. So what approximate range queries are is a bit different, is because this can be seen as a extension of what Bloom filter do from point filter to range, from point queries to range queries. What Bloom filter do is to give you an approximate answer where you don't have false negatives, but you can have false positives about the answer of the filter. If you can have a false positive, so it can tell you with a certain precision, with a certain grade of error, if a key belongs to the set or not. But it cannot give you a false negative answer. So if the filter tells you the key is definitely not in the set, so it's definitely not into the set. You cannot have any false negative probability. And approximate range queries are the same, basically just on ranges rather than on simple points. What are adversarial queries? Well, we saw that when we started evaluating Graffiti and the other state-of-the-art range filters, what we saw is that previously of Graffiti, what we had were mainly heuristic range filters. So what is a heuristic range filter? It's a range filter that answer approximate range emptiness queries, but cannot give you a bound on the error rate of the false probability, on the false positive rate probability. And since these range filters cannot provide you any guarantee, then you can build an adversarial workload that basically makes them useless because it draws the false positive rate straight up to 1. So if the false positive rate is straight up to 1, so basically you have no filtering. And you can imagine that what we use this data structure are mainly since they use very low memory, they can be kept into main memory, and you want to use them to guard the access to the disk to avoid useless IOs on disk. So what we do is that when we have a query on our system, we first query the range filter or the point filter that is in memory, and then if the range filter tells us that yes, the range or the key is probably there, then you go straight to the disk and you perform the actual query. And so if you can build adversarial workload on top of range filters, you can build certain kind of queries that drives the false positive rate straight to 1, and you're basically providing no filtering. You are allowing your adversarial, or maybe not even adversarial, you're giving them free IOs on your system. And we also saw that these adversarial workloads, what we have for adversarial workloads on range queries are workloads where the range is very close to the input keys, which is pretty normal, no? Because when you want to do a range query, you basically ideally, you are going to query a range that is close to your input set. It's not completely on the other side. So the more that this range goes close to the input keys, the more this heuristic range filters, they just provide no filtering at all. So that's why we wanted to provide a solution that we call it robust. And so what Graffiti can do is, actually, what Graffiti does is that you provide basically a false positive rate, you provide your input set, and that's it. You have a measurable way, and you have a measurable way to know what's going to be your false positive probability when you perform a query.
Nice, cool. So I'm just going to run through that and try to recap it so I've grasped it for you, Marco. So going way back to the start of your answer there, we were talking when we were actually introducing what range queries are. To give, I guess, a concrete example, you can tell me this is, I'm thinking this, obviously, my go-to example was footballers. So I've got a list of every Premier League player and their age, right? And that's my kind of a set of values. And then I guess my range query would be, go and get me every player that is between the ages of 21 and 23, right? That is basically it. Kind of way that one of those queries you would potentially go to that set of inputs and run that query over it, right? Would that be a good example, or?
We run the range queries on keys, straight to the keys. So imagine you have the input, your input set is the date of birth of football players. So you want to know what football players. So you want to know if a football player is born between 1997 and 1998. So that's basically a range query.
Cool. Gotcha. Cool. And then the problem here is that so to kind of go for what the false positive is, that it's always going to tell me when something is definitely not in that range, but sometimes it's going to say, hey, this is in there when it's potentially not in there, right? That's what we mean by the false negatives, right? Or the false positives. Yeah. I always get my false positives and false negatives the wrong way around, Marco.
Yeah. See it in this way. When you perform a query, it can tell you it may be in the set. It may be true, or it can tell you is definitely not there.
Gotcha. Cool. And then we've got this bunch of adversarial queries, which can kind of really because these exist in the state of the art stuff, use these heuristics, right? And they have basically no bound on the errors. So if you kind of get your queries set up in a certain way, that this could basically drive that whole thing to
Yes.
and it's useless, right? Because it's saying everybody, you have to go and check everybody again, essentially, because it's saying everyone's possibly true, right? Possibly in the range, in the set, sorry. Cool, and that's bad because we use this thing for performance, and then we're not getting any gain from it. So yeah, that's where Graffiti comes in. So let's go through the design of Graffiti then, and tell us how it actually managed to achieve this goal of not having the issues that the current state of the art approaches have.
Well, our approach basically is it starts from one of the first theoretical paper in the field. It's a paper published by Goswami, and it gives us, this paper proves the theoretical lower bound of the problem. So it proves you that you cannot achieve range filtering approximate range filtering on a certain number of keys for a certain length of the query without using at least that number of bits. So it's basically a lower bound of the problem. In that paper, they also propose a solution for the problem that uses optimal space and optimal time. In that solution, they use carefully crafted hash function to reduce the universe size from the original universe where your input set belongs to a reduced universe. And then they store that reduced universe into a very complicated kind of data structure. They do all the theorems, the lemma, the proof, and whatever, and they prove that this data structure is optimal for the problem. But it's very complicated, and there is no implementation for it anywhere, because it's mainly theoretical, and there is no way for implementing it in an efficient way. So what we did is to take that approach, but changing the underlying data structure, using a different type of data structure that it's really fast, it's really performant, and we have implementation for it. But basically using the same ideas of reducing the universe size through hashing, store the input, the hashed set of keys, and then performing range queries on top of that. And what we proved is that using this data structure, the famous Elias-Fano data structure, we achieved same optimal space and optimal time. Actually, we even have a better space if we go and check for the lower order terms of the formula. But yeah, we managed to implement it, and this is where this approach comes from.
Nice, cool. Before we go on to talking about how performant it actually is and discussing the results of your evaluation of whatnot of Graffiti, there was another contribution in your work that wasn't the only thing. There's a thing called bucketing. So it might be now quite a good time to tell us about bucketing as well and how that fits into this landscape.
Bucketing is another contribution. What we said with Giorgio and Paolo is that, okay, we have a heuristic range filter, we have robust range filter as well, so we have Graffiti. But since the design of the heuristic range filter that we have right now, it's very complicated. They have a lot of tricks, a lot of parameters, a lot of stuff that you have to be careful about. But maybe some system engineer, they still want to use a heuristic range filter on their system because of a lot of reasons. Can we design a heuristic range filter that is way, way simpler of the state of the art that we have now? So and then we came with the bucketing. which is basically simple. What we do is simply to map the input set into buckets. So we divide the universe into buckets of fixed length, and we basically store 1 if at least 1 key falls in the bucket, or 0 otherwise. And then we have a bit vector, and we can compress that bit vector in an efficient way. And that's what bucketing is. It's a heuristic range filter which suffers of adversarial queries, correlation, and everything we told before, but it's way, way simpler of what the other state-of-the-art range filter do.
Cool. So let's talk about how bucketing and graffiti obviously compare to the state of the art then. So the first thing probably good to tell us about how he actually went about evaluating these two algorithms. What was the actual setup of the experiments you ran?
Okay. First of all, the experiments, of course, are important, but there is a careful theoretical evaluation of them. Mm-hmm. So first, we did the theoretical evaluation, and then for the experiments, we used classical datasets that are used in this kind of with this kind of state-of-the-art range filters. So correlated and uncorrelated datasets, where for uncorrelated we mean that keys and ranges there is no correlation between the ranges and the keys, and with correlated, of course, the opposite. And of course, it's important to say that we didn't compare heuristic range filter with robust range filter, because it's basically like comparing apples and oranges. They do different purposes, and it's not fair to compare them. So we divided the comparison between heuristic and robust. We compare bucketing, of course, with heuristic, and graffiti with the other robust range filters. We used synthetic datasets, as I told you, with uncorrelated, correlated ranges, and also real world datasets like the Facebook IDs or OpenStreetMap positions and this kind of standard datasets. And then we tested the main things, such as query time, construction time, and false positive rate. And also the false positive rate as the correlation increased. So, and as we thought, there is no actual, you can see the actual difference between heuristic and others, and robust range filters. So even if we have some sort of heuristic range filter that can in some sense deal with correlated workloads, they increase exponentially their query time. So this makes them, I don't know, I would say a bit useless in those kind of workloads. Yeah, that's it.
Cool. So yeah, let's put some numbers on these experiments then, Marco. So give us the rundown. So how much better are graphite and bucketing compared to the other state-of-the-art approaches for heuristic and robust range filters? What's sort of magnitude of the performance gain?
Well, if we speak only for graffiti, and we take the false positive rate, we have a comparison of almost 2 orders of magnitude better for graffiti. We compare to the other state of the art for what concerns the false positive rate, and almost up to 90 times faster than the other state-of-the-art range queries. For what concerns bucketing, what we saw is that it basically matches what the other heuristic range filter do in terms of false positive rate, but it does that with up to 2 or 3 magnitude of time, in better time. So yes, so up to 2 up to 2 to 3 orders of magnitude less in both the query time and construction time.
Nice. So yeah, clear win on all fronts then. So that kind of leads into my next question then of, are there any situations still now where either Bucketing or Graffiti would still not perform particularly well? Like, what are the current limitations still of this approach, of these approaches?
So this kind of data structure, they perform really well in LSM trees environments. So in LSM trees database, that's why they're static data structures. So you exploit the fact that when you merge different runs in LSM trees, you have to rebuild everything. So you rebuild also the data structure. It's not very suitable in dynamic environments because of this reason. But yeah, it will be definitely a nice future work to try to design and implement dynamic version of it.
Yeah, that's always one of my questions as well, Mark. Like, where do we go
Yeah.
next with this line of research? And obviously that is maybe one making these data structures dynamic so they can work well in a dynamic environment. But are there any other particular interesting areas of research you think that could follow from this work?
This kind of data structure has been also used in research, just for research purpose in other fields like query auto-completion and so on and so forth. But I don't think they are completely suitable for this purpose, still for the same reason, because they are static data structures. So when you change the set, you have to rebuild everything. So, and this has a cost. So if you can pay that cost, perfect. You cannot achieve anything better because you are doing with Graffiti, you're basically lower bound. But maybe you want to, with the current state of computer architectures and storage, you are able to pay something in terms of it's okay for you to pay something in terms of page space to store. It's okay for you to pay something more for about the space, but have something more dynamic that you don't have to rebuild every time that your set changes. So that's why they're mainly exploited in LSM trees kind of databases.
Yeah, cool. Another sort of question that's kind of been bouncing around my brain whilst we've been talking is about the kind of adversarial queries in the wild, I guess is probably the way to phrase it. And how common would you see these sorts of query workloads appearing in production systems and sort of exploiting the bad path in a way, right? Like, is it something that we see frequently?
Well, imagine that you have a database that stores the identification, the IDs of your registered user in your system. So since they pick a point in the universe space, so what probably a user wants to do is it's a normal behavior of the system to query something that it's close to to those kind of IDs. Something that it's not completely, if you have your IDs between 1,000 and 5,000, don't want to go 30,000, right? So the closer you go to those input keys, the higher is the correlation. The higher is the correlation, the higher is the false positive rate that increases when range filters cannot deal with those kind of workloads. So yes, basically it's what is supposed to be a normal behavior of a system. Going the closer you can go to the input set.
Cool, yeah. I guess sort of going on to my next question then would be, obviously we always like to talk about impact, and impact sort of one of the kind of key things that we like to talk about on the podcast. Has Graffiti had any sort of impact in the real world in the short term? Are you aware of any systems, maybe LSM based systems that are thinking of adopting this, or yeah, and kind of longer term, just two questions for one for the price of one here. What sort of impact do you think graffiti can have in the and bucketing in the future, long term?
Well, for sure they are used into modern databases, into modern storage databases. And you also have to consider that you can use range filter to answer also point queries. So you basically don't have to have in your system, but if you have a bloom filter and a range filter both in your system, because you can basically use a range filter to answer a range query where the size of the range is 1. So it's a point query. I don't know at what extent this kind of filters are preferred over, I'm speaking about heuristic range filter, preferred over classical solutions that can be Bloom filtered or prefix Bloom filters for range queries, which do not provide any for what concerns prefix Bloom filter. They still have the same problem about adversarial workloads and so on. But maybe since now we have a solution that can provide robustness in this kind of topic, maybe it can be something that it's going to be implemented in future systems, or at least a good benchmark will tell us if it's worth or not to replace maybe more trivial solution.
On the implementation effort, so of your past, how hard was it to implement this? Like, what was the sort of, how long was the engineering effort, I guess, and like kind of going from okay idea to actually implementing the thing, getting it working correctly, and being able to evaluate it? Was it quite a long period or easy or?
No, it wasn't a long period. It's a simple implementation. There is a GitHub repository. You can check it. It's really simple because, and I think this is its strength, because keeping it simple, sometimes we want to overcomplicate things that they don't need to be complicated. So sometimes we just stop and maybe reflect a little bit more. We can find easier solutions for tasks. I'm not saying that we don't need complex solutions for a lot of topics, but sometimes it may be an overkill for some sort of problem.
Yeah, I completely agree with that message there, Marco. There is sometimes sort of that inherent sort of desire to like more complex means better in a way sometimes.
Yeah.
Which I think it's kind of in some level maybe like human nature. I think we're all guilty of it, but having a clean solution that achieves the same goal that's simple is like, yeah, obviously that should be better, right? But sometimes we always reach for the more complex thing, right? Or we think we should be doing. But yeah, it's interesting that. Cool, yeah. So I guess while working on this project, was there anything that sort of jumped out as a surprise or was quite kind of like, huh, that's really interesting, while you're working on graffiti?
Well, it gave me the chance to actually, because I was a fresh grad from my master, so it gave me the chance actually to explore a lot of research, to see how things are done, in this kind of environments. So how research is actually done, and how what we need to do things properly. So yeah, there's been a bit of a shake for me, because I was a master student, and then now you try to write a paper that is going to be published in one of the best conference in the world. So yeah, it was then the joy of your first paper. My surprise was to see how the world between when you go out from the university, when you actually start to state of the art works is different.
Yeah, I mean, it's a very similar experience sort of when you're first exposed to the sort of level of rigor and that sort of scientific process to go through to be actually get something that is good enough level to, like you say, be published at one of the leading conferences in this research area is it's an experience, right? It's challenging, but I think rewarding in the long term. But I mean, you started off great, right? What was a one paper, one SIGMOD paper? It's a pretty strong record, Marco. So yeah, maybe it
Yeah.
started off well.
Like when the athletes, they just retire as a winner, will just retire. One paper, Simon, completely.
Yeah, job done. Yeah, I've got
Uh,
my Olympic gold basically.
yeah, been there, done that.
Got the t-shirt, yeah. Cool. So going over then, so like talking about, I think maybe we mentioned this a little bit earlier on when you kind of was telling us about how you ended up being interested in database research. But this origin story of this paper, so obviously there was an existing sort of paper that was sort of like a bit of the motivation behind this, and you kind of brought this data structure along and sort of made it real. How did that actually come about? Yeah, tell us a little bit more about the backstory of the paper, I guess.
Well, uh, I was looking for a master thesis,
Mm.
and that's the beginning of the story.
Yeah.
So Giorgio, my one of my co-author, so Giorgio Vinciquerra, he read the Goswami paper that we were discussing before, and he saw that maybe the existing solutions, they weren't exploiting at all that kind of result. So, and he told me, maybe we can do something about it. We can try to read carefully that paper, that Goswami paper, and see if we can do something that takes into consideration what they did. Because they propose a solution, they are not able to implement it, and the robust range filter solution we had at the time that were implemented were inefficient in terms of theoretical were inefficient in terms of theoretical bounds. So that's how it started. Then it continued with my master degree, and then with my other advisor Paolo Ferragina, we discussed if it was possible to transform that master thesis into a paper. And they proposed me to do a PhD in Pisa, but I was more interested in trying to explore the industry field rather than continuing on research. So I did a 6-month research fellowship, a 6-month research fellowship contract, and yeah, that's basically what I worked on.
Cool. I guess sort of as we were talking about you going through the scientific process and sort of getting familiar with how to sort of produce a research paper of top quality, there's obviously part of that is generating ideas and then deciding which ones are actually worth spending time working on, which ones need to go straight in the bin. So I don't know, Marco, if you have a personal approach that you've developed over this experience of like generating ideas and then choosing ones which you think have actually got some value.
Well, this is not an easy question. So I think that you can have all the thinking process. So say yourself, okay, I will just stop here on this desk and I will just try to think and think and think until something comes into my mind and I come up with a great idea. But in my experience, when you have the moment when you have an idea, it's a very short time frame. So it's something that just comes into your mind. You have that moment when you stop there and you reflect and you say, okay, yes, maybe this can work. Maybe can be a good approach. And maybe it comes in the most desperate time of your life, under your shower, I don't know, when you go out for a walk. But yeah, most of the time it in my experience, I wasn't at the desk when I had the best ideas and my best creative process. But
Yeah. Yeah, no, that's true. It comes to you when you least expect, right? And I think that sometimes is if you try and force it and sit there, like you're saying, lock yourself in a
yeah,
room, it's often almost antagonistic to generating ideas. Like it has the opposite effect. Your brain just kind of goes, "Boo," and it's like, I ain't going to do anything. But yeah, no, that's really cool. So yeah, Marco, we're at the time for the last word now from the podcast. So what's the one takeaway you want the listener to get from this chat today?
my key takeaway is that in my experience, when we have simple problems where we will, my key takeaway, I would say that where we have, when we face simple problems, we don't have to overkill the solution. Usually the best solution, in our case, the optimal solution is simple. So usually simple problems have simple solution. Let's try not to overkill solution just for the sake of it.
Yeah, I think that's a great message to end on there, Marco. Thank you so much for coming on the
Thank
podcast.
you. Thank you.
It's
Thank
been
you for
great.
having me here.
More than
It's been a
welcome.
pleasure.
Whereabouts can we find you on social media? Are you active on any of those platforms that people can engage with you?
You can find me on LinkedIn, I think. On LinkedIn and my GitHub. I don't use much other kind of social medias.
Cool. That's the healthiest thing to do, man. Honestly, yeah. Cool, fantastic, and yeah, and we'll see you all next time, listeners, for some more awesome computer science research.
Thank you.